Well, that's where it belongs.
Like Superman.
My alma mater, and Stuart. Let me know when you're around. Okay, so I'm really happy that today we have visiting from Harvard, Stuart Shieber, who's been there on the faculty since, I think, 1996?
89.
In 1989. You got tenure in 96.
That's
right. Okay, one of the few people to do so from inside.
Not so infrequent anymore.
Well, they're starting to bend their way. You were trailblazing. Dr. Shieber's worked in a number of different areas in NLP, but he's looked especially over the years at foundational issues. A number of you probably know his book from the late 80s with Fernando Pereira called Prologue in Natural Language Analysis, and which basically showed how you could look at lots of different natural language algorithms, for example, parsing in different grammar formalisms as proof systems. And he did a bunch of the work around that time also in unification-based grammar formalisms, as well as the more lightweight formalisms like GTSG. And I don't know, I won't try to list everything that he's done, but you should know that outside of NLP, he's also worked in a number of areas, including user interfaces, for example, most recently for graph drawing. And I just found out, talking to him before the talk, that he's got a company that does document image compression. So a man of wide interests, and today talking about tree transduction. And those of you who are in the NLP reading group may remember that we used some of his slides on tree transducers when we were going over that topic last year.
Well, thank you very much for the opportunity to talk to you today. I wanted to use this time to present some work in progress that I'm doing on frameworks for tree transduction that I'm hoping will be general frameworks for a wide variety of natural language applications. I'm going to start by trying to give some motivation for why I'm interested in this problem, and then talk about some of these kinds of framework issues. So many of you are probably familiar with various kinds of low-level natural language processing tasks, which you really can think of as some kinds of string transformation tasks. And I'll give some examples in a moment, but in essence, over the years, there's developed a kind of a universal formalism for these kinds of string transformation systems, namely weighted finite state transducers. This is a view that is probably most widely associated with now with AT&T, or it was until everyone at AT&T left. Now it's being dispersed in a diaspora across the country. But I'm interested in kind of farther down the pipeline kinds of natural language processing tasks, where you can think of the general form of the task as a kind of a tree transformation task. And I'm interested in what kind of universal formalisms there might be for that kind of task that are to tree transformation what weighted finite state transducers are to string transformation. Let me give you some ideas of what I have in mind. This is a screen dump from a system, Dragon Naturally Speaking, that you may be familiar with. So the command browser, Dragon Naturally Speaking, has a speech command and control subsystem that allows you to, in addition to dictating speech to be transcribed, allows you to control various kinds of applications like Microsoft Word with speech as well. So you can say things like select the next paragraph, make it bold, things like that. And if you think about that kind of application, how is it that you can make that work? You have to start with voice in the input, and out the back has to come some kind of command to make a word processor do its thing. Well, typically we stage the computation by taking the voice and turning it into a sequence of words, say, and then those words will be somehow transformed into the appropriate command. And the first part of that transformation, going from voice to a sequence of words, we can think of as going from one kind of string, a string of, say, some kind of acoustic, quantized acoustic events, to another kind of string, a string of words. And AT&T view, the kind of argument that I would make is that weighted finite state transducers are a kind of a universal formalism for that. Then the next step might be to take this string of words and convert it into a tree that gives the structure of the sentence. That's done by a process called a parser, and that's pretty well understood how that goes, so I won't say anything further about that. And now you have a tree that represents the structure of the sentence, and we need to convert that into a command. Well, what's a command? A command is really another kind of tree. It's a tree in the case of this particular application, this Dragon Naturally Speaking front end to Microsoft Word. It's a tree in representing a program in the programming language Visual Basic. It's actually how the system works. You convert the sentence into a Visual Basic program, which when executed selects the next paragraph or makes it bold or whatever. And the question is, what is the appropriate formalism, universal formalism for this kind of tree transformation that weighted finite state transducers is for string transduction? So let me say a word about the actual formalism that's used inside of Naturally Speaking, which before it was used in LNH's Voice Express, and before that Kurzweil's Voice Express. It's a system that we designed originally for Kurzweil that uses a kind of ad hoc deterministic tree rewriting to rewrite one set of trees into another, kind of a cascade of tree rewriting passes. And the way I initially got interested in this general problem of tree transformation was revisiting the design of this system to see if there was some general framework that you could use to figure out what we had kind of inadvertently tripped over when we built this system. Well, so there's that view of tree transformation for natural language command and control. And if you think about machine translation, you get a kind of a similar picture. You might start with some words, maybe use a string transducer to give you morphemes, parse it into some source parse, but then you have to convert it into the target parse. And you might think that that's some kind of tree transduction as well. A kind of a tree transduction that's going to have to do some pretty sophisticated transformations. For instance, this kind of a rotation that converts a tree of this structure into a tree of this structure, where the alignment doesn't respect the hierarchy. I'll have more to say about that in a little bit. Another application for this kind of tree transformation might be corpus normalization. Here's a description, for instance, of an algorithm that Michael Collins used to massage data before training his well-known statistical parser. It's a kind of a tree transformation algorithm. Here's Josh Goodman's description for normalizing trees in order to generate training data for his revision of the dot model. And you see different kinds of tree transformations that have to go on here. In fact, tree transformation is really ubiquitous in this kind of natural language processing task. We talked about the first three of these, but also you can think of database query construction, semantic interpretation, natural language generation, and so forth. All of these things are kinds of tree transformations. And so the question is, just as finite state transducers, especially weighted finite state transducers, can be applied to all kinds of low-level string processing tasks, is there a similar kind of universal formalism for this tree transformation work? What is to trees as weighted finite state transducers are to strings? That's the question I would like to answer. Unfortunately, I don't have an answer to that question, so instead I'm just going to ramble for the next 50 minutes about directions that we might go, about ideas that I do have so far. But by no means is there a final answer here. Okay, so let me give an overview for the rest of the talk, which is attempting to kind of approach this question of appropriate formalisms for natural language tree transformation. First, of course, the natural thing to do, string transducers are the right thing for string transformation. Maybe tree transducers are the right thing for tree transformation. Tree transducers have been known since about 1970 from the work of Thatcher and Rounds. So maybe that's the right thing to use. Well, the answer is no, and I'll tell you why that is. Why they aren't the right way to think about this problem. On the one hand. But on the other hand, I want to say, yes, they are the right way to think about this problem if you don't think about them directly, but you think about them in a kind of a second incarnation of tree transducers. A second incarnation described in terms of what are called in the formal language theory community bimorphisms. Not a very well-known characterization of tree transducers, but they allow you to generalize tree transducers in interesting ways, and ways which allow, for the first time, an integration of this theory of tree transducers with theory of synchronous grammars, which I'll talk about. And in particular, in a way that allows a new characterization of synchronous tree substitution grammars and allows even pulling into this same framework synchronous tree adjoining grammars. So I'll first talk about the tree transducers, then and talk about why they're inadequate, then describe synchronous tree substitution grammars, and describe the relationship to tree transducers through these bimorphisms, and then talk about some generalizations, generalizing to synchronous tree adjoining grammars, talking about weighting, making weighted versions of these things. And I hope by the end to convince you that although I don't have an answer to what the right formalism is, probably somewhere in and around bimorphisms is the right way to be thinking about it. That's my hope for the conclusion we'll draw. So let me start by talking about tree transducers, just to remind you how tree transducers work. So first I have to say a little bit about what trees are, and I'll use this kind of BNF format that people who are familiar with how programming language people do abstract syntax will be familiar with this kind of notation. So we start off with some set of symbols, each with an arity, and I'll use F as kind of the generic such symbol. And an F with arity M to form a tree will take some more trees, T1 through Tm, in the trees formed out of symbols in F, and make them children of F. So that's this little grammar tells you what all the trees are formed out of the symbols in F. Some of these symbols will have arity 0. That's what will bottom out this recursion. Okay, those are the constants. So for instance, if I have this set of symbols, S of arity 2, NP of arity 1, and so forth, I can build a tree that looks like this, or equivalently, we might want to write it this way. It's probably easier to understand. Okay, so that's what I mean by trees, and I go through it this pedantically just because I'm going to use this notation a lot, so you'll be familiar with it. It's a kind of little grammar of trees. I'm going to want to have some trees with holes in them, so I'll add trees not just based on some symbols, but also some variables. Set of variables x, and I'll allow these trees to be formed in the way before, but also as variables. So I have variables serving to mark some holes, and the variables will be given literally as x0, x1, x2, and so forth. So there's trees with holes, and now I'm going to move one step further on the path to tree transducers by introducing tree homomorphisms. We start with a kernel of a tree homomorphism. That's just a mapping that takes one set of symbols onto some trees with holes. So here's such a mapping. Maps F onto this tree that has symbol G with two children labeled X, the variable X. And here it maps the symbol A onto itself. Okay. So when we have a kernel of that form, we can use that to generate a tree homomorphism just by extending it homomorphically. So whenever we're going to build this homomorphism H, which takes a tree of some symbol applied to some subtrees, and the homomorphism applied to that tree we get by taking this tree that the kernel maps the symbol to, and replacing the variables with the homomorphic images of all the subtrees. So let's take this example. Here's the kernel, and we get these equations out that define the homomorphism. H applied to F of something is just going to be G applied to the homomorphic image of the something that's the child of H. And H applied to A is just A. So there's a homomorphism, and we can apply it to a tree. If we apply it to this tree, H applied to this tree, we get this tree. This is the homomorphism that maps every linear string of a certain number of F's onto a perfect binary tree of the same depth. Perfect binary tree over G, the same depth. Okay, so there's an example of a tree homomorphism. And we can, just as we defined trees with this kind of grammar, we can define the equations that give us a homomorphism with a grammar as well. And it looks like this. All these equations are of this form. They say, for some H, a fixed H, H of some symbol applied to a sequence of the right number of variables is equal to, and now I use tau for the right-hand side of the equation. The right-hand side is a very simple thing. It's just going to be some other tree. But we're going to allow at the leaves not just, it's a tree made out of these taus, but we're going to allow at the leaves not variables, but H applied to a variable. So you can see these things are of that form. Here we have a tree, but at the bottom, we have not only constants, but we also have these H applied to one of the variables that's defined on the left-hand side. People see what this grammar is saying. It's just a grammar that defines the kinds of equations that define tree homomorphisms. I should say this is not the standard way of describing tree homomorphisms, but again, I do it this way because the generalization to these other systems is going to be very direct. Now, when you have equations of this sort, we can talk about subclasses of homomorphisms. And I'll use, sometimes I'll use these symbols in the parentheses to denote these different subclasses. There are arbitrary homomorphisms defined by any set of equations of that sort. But then we might have a linear tree homomorphism, which is a homomorphism is linear if no variable occurs twice on the right-hand side of a rule. So this is not a linear homomorphism because x occurs twice. In a complete homomorphism, all the variables on the left-hand side have to occur on the right-hand side. So this is a complete homomorphism. Epsilon-free homomorphism, you need some structure on the output. The output can't just be a single variable, that is h of a single variable. And symbol to symbol means that there's some structure on the output, but it's exactly one symbol applied to h of some variables. So it's basically h of some symbol is some symbol of h. It's just replacing one symbol with another. And finally, a delabeling is a linear complete symbol to symbol homomorphism. All a delabeling does is replace the symbols without doing any copying or deleting of anything. It's reordering and replacing labels. So there's different kinds of tree homomorphisms. Now we want to go from homomorphisms on trees to transducers on trees. Just to remind you where we're going, by the way, in case you got lost in all of this stuff, I'm just reviewing classical tree transducers from the 70s with this slightly different notation, since it's going to be useful for the generalizations. Mostly just to show you how they're not very good for what we want to do. So that's where we're headed. But right now, we've got tree homomorphisms. We want to generalize them to tree transducers. And there's two ways of doing that. There's the well-known way, and there's the not very well-known way. So the well-known way is to add state to a homomorphism, have a homomorphism with state. The not very well-known way is to synchronize two homomorphisms. So here's the well-known way, kind of the classical way to do it. We're going to make this homomorphic mapping sensitive to state. So instead of having a single mapping, H, that we're defining with these equations, we're going to have a set of mappings. And traditionally, we don't use H for these mappings. We use Q, and we think of Q as representing a state. So here's an example where I have a bunch of equations defining not just Q, state Q, as it maps, but also q prime. What does q do on a tree of the form f of x, or on a tree of the form a? What does q prime do on a tree of the form f of x, or a tree of the form a? And what q does is it does this binary copying, but on its left branch it uses q prime. On its right branch it's again use q to do the binary copying. But this left branch uses q prime, and what q prime does is it just copies its input to its output. So q prime of f is f of q prime. Q prime of a is just a. Just copies the output, input the output. So we can see how this system of equations, that is to say this tree transducer, operates on a tree. Here's the tree we start with, and we start by going to know what is q of this tree. So q of f is g of q prime q. So we have g of q prime of the first child and q of the second child. Q prime of f is f of q prime. Q of f does this g thing again. And we keep pushing the states down until we end up with the transduced tree. So a tree transducer is just a system of equations like this. A tree homomorphism under this view is just a tree transducer without state. That is to say, it has one, when you have one state, it's like not having any state at all. Okay, so this is a classical root to frontier tree transducer. It's a tree homomorphism with state. And here is, remember, this is the form of equations that define homomorphisms. We always use H here. To define transducers, instead we use Q and various QJs on each of the variables, where Q is from some set of states. So that's the only difference. That's the generalization from homomorphism equations to tree transducer equations. When the tree transducers compute the identity function over trees, we call them tree automata. That is to say, each of the equations is linear, complete, symbol to symbol, where it's the identical symbol on both sides, and order preserving. So they're kind of trivial equations. And they define the regular tree languages. That will be useful to know. So tree automata, regular tree languages are just defined by these identity tree transducers. By the way, by analogy, you can think of finite state automata as just being the identity finite state transducers. It's the same idea. Now let me take a quick digression talking about why these tree transducers don't really work the way we might like. And one simple way to see this is to look at rotations. What I mean by rotations is trees that we might want to transform from this form to this form, where the mappings don't respect the hierarchy. So this is an English sentence, I like cake, with this structure, and in German you say something like the equivalent of cake is pleasing to me. So this subject noun phrase in German corresponds to the object noun phrase in English, and vice versa. The subject in English is the object in German. So the structure doesn't quite work out. And we'd obviously like to, this is a kind of a tree transduction, we'd obviously like to be able to capture this kind of thing. Here it is in kind of idealized form. Here we're combining x and y together first and then with z, but in this side we combine y and z together first and then with x. So can we write this kind of tree transformation? We might want to do this for various reasons. So the so-called translation divergences in machine translation, semantic bracketing paradoxes in interpretation, corpus restructuring, like I showed at the beginning. All of those things you can think of as different kinds of rotations of various sorts. What we'd like to do is have some kind of transformation that relates this kind of tree, f of g of x, y of z, where x, y, and z are variables over whole subtrees, to f of, and now we want to take the image of x, g of the image of y, and the image of z. We'd like to write this kind of thing down. But you'll notice this is not an equation of the form that I gave the grammar for before. And the reason is that on the left-hand side, it's not some state applied to a single symbol. It's some state applied to a whole tree. So there's a question, can you even, so this, you can't, this is not, as stated, a set of equations that, or an equation that's part of a tree transducer. But is there a way to do it? Well, it turns out that there is, but you need to do a bit of hacking. And so here is an example of how to do it. We're going to apply, we're going to make a transducer with start state Q that takes f of two arguments. These are two variables, x and z. Here I've given the x a subscript gxy to remind us that x better be of the form gxy. That's the intention. The intention is that x is something of this form. And we're going to build something of the form f of something involving this gxy thing. In fact, the x part of the gxy. And I'll have a state q1 which extracts the x part of the gxy. And then g of something else involving this gxy, namely the y part, and then q of z. So what do q1 and q2 do? q1 takes something of the form gxy and extracts x. q2 takes something of the form gxy and extracts y. Well, you have to kind of decompose it in this way, and it's really annoying. Not only is it really annoying, what we require here is an equation that's nonlinear. It might seem a little odd that we require nonlinearity because somehow this rotation looks very linear. There's no copying going on. We start with one copy of x, y, and z. We end up with one copy of x, y, and z. Why should we require nonlinearity? It's a sign that there's something not right in how tree transducers work. Yeah.
And the latter two rules are neither complete nor epsilon free, right? So
that's right.
So the first rule copies stuff, and then the second one
deletes it. Yeah, right. And that's neither of those seems to be intrinsic to this very simple kind of rotation. So there's a sign that something is wrong. So that's the traditional way of doing tree transducers. And now I want to do the less traditional way, the bimorphism way. Now instead of adding state to a homomorphism, we just take two homomorphisms and we synchronize them. There's no state. A bimorphism is just a construction where we take a regular tree language and add two tree homomorphisms, an input and an output tree homomorphism, that apply to the trees in this tree language. So the pairs of trees that are related by this bimorphism is just the trees you get by taking some tree in the language and applying the input homomorphism and the output homomorphism to that tree. Another way of thinking about that is you take the inverse image of the input composed with the language composed with the output. So here's a little picture. We take some tree, we apply the two homomorphisms, we get two other trees, and those two trees are related by this synchronized pair of homomorphisms. Now, that's a general notion of bimorphism, and we can have subclasses of such bimorphisms by restricting the homomorphisms that we use for the input and the output in various ways. So I'll use this notation, B of two arguments, where the first indicates the type of input homomorphism that we want. Maybe it's an arbitrary one or a linear one or whatever. I'll use these symbols here. And similarly for the output homomorphism type. Now, let's look at the relationship between tree transducers and bimorphisms. If you think of one of these equations that defines a tree transducer, a step in a tree transducer, you can think of it as mapping some symbol with its children onto the homomorphic images of those children placed in the context of some tree with variables. And these get these little pieces, these little rules get put together, pasted together by making sure that the states match. So here we start with Q, and this first child is going to be Q1 of something or other. And then we're going to have some rule that says Q1 goes to whatever. So a derivation tree that puts these rules together is actually a regular tree language. And then if we extract from a derivation tree that puts all these rules together just the F part, that's a simple homomorphism. We can go from a derivation tree where the nodes look like this to just F. We get the input tree, and if we pull out the C part and paste those together, it's another tree homomorphism. We get the output tree that's related by this derivation. And the thing to note is that the mapping from this derivation tree to F is a delabeling, but the mapping from derivation tree to this C is arbitrary because we've made no constraint as to what C can be. It can be any tree. That is to say that a tree transducer relation is identical to a bimorphism where the first homomorphism is a delabeling and the second is arbitrary. So there's the relationship between tree transducers and bimorphisms. Tree transducers are this kind of bimorphism. That's kind of a hand-waving proof that that's all you get in this talk is hand-waving proofs. Okay. So why is this kind of bimorphism problematic? You can start just reading off of the thing various. For instance, you immediately know that that these are not symmetric. I mean, you can just tell from looking at it. And we saw already that they allow exponential growth, which tells you also immediately that they're not closed under composition. Okay. So this is just another way of this kind of bimorphism, just another way of thinking about exactly the same thing, these tree transducers. But once we have this generalization where we can form bimorphisms of different kinds of homomorphisms, we can start experimenting with other alternatives. For instance, if we wanted something symmetric, we could restrict the output homomorphism also to be a delabeling. That's clearly going to be symmetric now. Unfortunately, it's not very powerful. Not nearly expressive enough, you're not going to be able to do rotations, for instance.
Does that give you closure and composition of the second?
This will give you closure, yeah. This will give you closure of composition. Suppose we don't want to go so far, but we're willing to restrict to things being linear. Well, that's linear growth. You don't have this exponential growth, but you can't even express rotations now anymore. So that's not going to work. So restricting the output homomorphism isn't really helpful. So now I'm going to start all over. Forget tree transducers. I want to introduce a completely different framework, synchronous tree substitution grammars. Of course, at the end, I'm going to tie the two together. But for the moment, I'm just going to imagine we're starting all over. We'll start with context-free grammars now and work our way up to synchronous tree substitution grammars, just as I started with trees and worked up to tree transducers. So context-free grammar, you know, is just a formalism for plugging together little pieces of tree of depth 1, plugging them together with substitution of like non-terminal. So this NP, maybe plug in this NP tree, and forming trees out of them. So here's a little derivation. I take this little treelet and put in this one, and then put in this one, and we can keep going on in that way, substituting one tree for another. Again, not perhaps the traditional way of describing context-free grammars, but you can see that that's really identical to rewriting way of doing things. A synchronous context-free grammar is just a system where instead of little treelets, we have little pairs of little treelets. So here's an example. We have this pair, the verb eat and the verb esse, the noun phrase cake, the noun phrase kuchen. And we can put these together. You'll notice there's these links between nodes in the pairs. A link for the V's and a link for the NP's. And what the links say is when we do an operation at one end of the link with an element of a pair, we have to do an operation at the other end of the link with the corresponding element of the pair. So we can plug in this pair into this pair, and we'll get this pair of trees, eat cake and esse Kuchen. Now, with synchronous context-free grammars, we can't do much. We can't, for instance, do these kinds of rotations for obvious reasons. They just don't line up. So we can diagnose the problem as being one of having the domain of locality in these trees we start off with as being too small. So maybe we can broaden that. Maybe we'll allow bigger trees in this initial set of trees. And so now this is not context-free grammars anymore. This is tree substitution grammars. The only difference is we still have substitution as the operation. We're just allowing the elementary trees to be bigger than depth 1. So we'll have maybe these would be the 3 elementary trees, and we'll plug them together like this, again with substitution, and come up with this derived tree. And then we get as it turns out, no additional expressive power over context-free grammars, but we do have this expanded domain of locality. One thing I ought to mention about these tree substitution grammars is that unlike context-free grammars, there becomes a non-trivial relationship between the derivations of trees and the trees that are derived. In the case of context-free grammars, those are essentially the same thing. They're isomorphic. But here they're not. Here's a derivation tree. It says, we'll take this tree here. Where is it? This tree here. It introduces the verb ist. And we're going to substitute in this tree and that tree. And you'll notice the shape of that is a nice, small, depth 1 tree. But the tree derived is this much more complicated thing. So these are no longer isomorphically related as they are for context-free grammars. In fact, we'll see exactly how they're related in a second. So there's our tree substitution grammars, and now comes, I guess the second has arrived. Here's how they're related. Tree substitution grammar derivation. This relation between, I'm just going to assert this, but it's true, you'll have to trust me. The relation between derivation trees and derived trees is a linear complete tree transduction relation. And in fact, for the grammar on the previous slide, here is the relation. It starts with this start state QS, which applies to a tree that looks like this and gives you S of whatever this tree, whatever this subtree, the image of this subtree is. That's QNP of X. But requiring, because that's an NP here, requiring that that tree be rooted at NP. And then there's a VP and a V with ist, and then the homomorphic, the transduction of Y, but again requiring that that be rooted at NP, and so forth. So you can just write down for the grammar exactly what this relation is. And it turns out that because of the details of how substitution works, this is always going to be linear and complete. It's a linear complete tree transducer. Another way of thinking about it is, you can think about it as the composition of a linear complete tree homomorphism. Where is it? Here. A linear complete tree homomorphism composed with this regular tree language. So we'll divide it up. First, we'll check that the derivation tree is of the right form, obeys the constraints, that it's in this regular tree language, and then we'll apply a homomorphism. So the homomorphism itself doesn't have to do the checking. It's another way of thinking about it. You can decompose it that way. Okay, so just remember that it's a regular tree language composed with a linear complete tree homomorphism. That's tree substitution grammar derivation. So what's the payoff? The payoff is when we synchronize tree substitution grammars as opposed to synchronizing context-free grammars, you get this ability to do lots more. In particular, you can do rotations. Here's a grammar with two verbs, eats and ist, paired, synchronized, cake and kuchen, Kim and Kim. And we have a derivation that gets you Kim eats cake being paired with Kim isst kuchen. Okay, but the payoff is we can do this likes and gefällt thing where we invert, by changing how the links work, we can have the subject of likes be the object of gefällt and object of likes being the subject of gefällt, and get the right do a derivation like this and get I, I guess this should be I like cake and Kuchen gefällt mir, okay, being paired together. Now, this is the derivation tree for the synchronous tree substitution grammar. Recall that this can be recognized as well-formed, just a regular tree language. And then, to get the derived tree, that's just projecting this derivation tree onto its first component, say. That's a tree homomorphism, linear complete tree homomorphism. And then applying tree substitution grammar derivation, that's just a linear complete tree homomorphism. We compose the two, that's still a linear complete tree homomorphism. So what we end up with is something that describes the tree relation of this synchronous tree substitution grammar is just a bimorphism where the input and the output are both linear complete homomorphisms. I went through that very fast, but here's the thing to remember. Synchronous tree substitution grammars are also characterized as a bimorphism, namely this one. Bimorphism where both the input and the output are linear complete tree homomorphisms. So what I showed you so far was that for every synchronous tree substitution grammar, you can generate such a bimorphism. You'd also like to go the other way around. You'd like to say for every such bimorphism, you can construct the corresponding synchronous tree substitution grammar to show that they really are the same thing. And that proof of that is considerably more subtle. And I have a paper in the last TAG conference which goes through a kind of a sketch of a proof. But I won't go through it now. It's a little bit tricky, but you can do it. So that is to say that STSGs, at least under this conception of them, Jason has a slightly different conception of them, are this kind of bimorphism. Okay, but now things look a little bit better because here's a kind of bimorphism which is symmetric. There's linear growth, everything's linear. I believe, although I haven't proved, but I think it's true, that this system still isn't closed under composition, unfortunately. But it's closer. I don't know what it means to be closer. I have hopes. But the interesting thing is, even though everything is linear, you can easily express rotations. It just has a nicer feel for the kind of thing that you need to do in these kinds of problems. And it points the way. It points the way. Instead of thinking of things in terms of this top-down rewriting, classical tree transducer way of thinking about things, thinking about them in terms of these bimorphisms where you have lots of ability to manipulate the separate homomorphisms gives you much more flexibility and can serve as a general framework. In the last few minutes, let me talk about how this general framework can pay off in kind of absorbing all kinds of other formalisms too. We've already absorbed into this general bimorphism way of thinking classical tree transducers and some subcases and synchronous tree substitution grammars. But we can go further as well. Let me talk about tree adjoining grammars. Some of you may be familiar with tree adjoining grammars. Tree adjoining grammars extend tree substitution grammars with an additional operation of adjunction. In the set of elementary trees, we have trees of this form where one of the frontier nodes, a single frontier node, is labeled with the same non-terminal as the root. We call it the foot. And so it's incomplete at its frontier in some sense. And the way it's inserted into another tree is not by substitution, but rather by a kind of a splicing operation. So for instance, if we wanted to take this tree and splice it in at that node, we would split the tree here and plug in that tree with the root and foot. So if we have a derivation of this sort, this tree, I'll call this tree alpha and this tree beta, we can splice in beta at its own center node, right? One copy of it inside another copy of it, forming a tree with an even larger tree, again with a single root and foot. and splice that into alpha right here, and we'll get this tree where I've tried to color code, perhaps not particularly effectively. This beta, the innermost beta, is this tree. This beta is that piece plus that piece. Alpha is that piece up here with the red line and that piece down there. So it's kind of pulling things apart. And you'll notice that if you just look at the string generated here, we get A, B, B, C, C, D, D. And if we keep making longer and longer, larger and larger trees, you can see the language generated by this tree adjoining grammar is A to the n, B to the n, C to the n, D to the n, which is not context-free language. So you immediately tell that unlike tree substitution grammars, we can go beyond context-free languages with this formalism. So what I want to do now is I want to do for tree adjoining grammars what I just did for tree substitution grammars, that is form a synchronous form of them into this bimorphism framework. To do that, I actually have to give you a new definition of the relation between derivation trees and derived trees for tree adjoining grammars. So let me do that. You recall when tree transducer equations looked like this. That's the grammar I gave before. I want to extend this to form what I call embedded tree transducer equations. I'm going to extend the power, and I'm going to extend the power by having these states take a single argument that's a single argument tree that's used in a very formulaic way, a very simple way. Okay. So every time I have a state, it takes an additional separate argument. I put in angle brackets. And the argument, so the left-hand side, the argument is x0. And on the right-hand side, literally, that single variable, x0, is the only variable you can put there. On the right-hand side, I can either use x0, or when I apply some other q to one of the variables xi, I can put any tree as the argument, any tree that's formed in this way, hereditarily. So embedded inside here could be some bunch of tree with some x0s and some q of taus and so forth. Okay, so this is the only place I'm extending the definition. I'm allowed to postpone a tree, basically, by passing it into a state and have the state percolate it down and add stuff to it. And then at the end, I can just use that tree that I built. Here's as it turns out, is an embedded tree transduction that implements the mapping from derivation trees for this grammar to the derived tree. I won't go through it in any great detail. In fact, I won't go through it at all. You'll have to trust me. But you can kind of see here I'm taking QA of x0, and here I'm passing QA some big tree that actually has x0 in it, applied to the variable x1. And here's a derivation. I won't go through the steps, but it satisfies these equations. I take the tree alpha of beta, and I end up with something with 2 A's, 2 B's, 2 C's, 2 D's when I'm done. Okay, so it really does have this, and obviously you can see immediately there's power introduced here because you couldn't have done this with a tree homomorphism. So, and again, this embedded tree transducer could be split into a regular tree language and an embedded tree homomorphism. So I can do the same trick. I can say tag derivation is just regular tree language composed with an embedded tree homomorphism. And now, since derivation trees form a regular tree language and the derivation relation is, as it turns out, linear incomplete embedded tree homomorphism, synchronous tags now have a bimorphism characterization too. Namely, where the two things that used to be homomorphisms are now embedded linear complete homomorphisms. So synchronous tag falls into this class too. In fact, if you go through lots of different formalisms that various people have proposed at various times in the literature, a lot of these are from the kind of syntax-aware statistical machine translation literature. They all boil down to bimorphisms of one sort or another. Many of them are these things that are basically synchronous context-free grammars, reinvented in various ways or restricted in various ways, kind of notationally restricted if not expressively restricted. But other things too. Grail and Knight in the last HLT had a paper about using tree transducers for machine translation, where they generalized these classical tree transducers to things that allowed linear complete homomorphism. They didn't describe it this way, but that's essentially what they did. Then they gave algorithms which they claimed were for XR, but they actually were for this subset, which you'll notice is suspiciously close to synchronous tree substitution grammars. So it looks like they've almost reinvented synchronous tree substitution grammars there. And the nice thing about this way of viewing things is you suddenly start seeing the relationships between all these things that people are doing. Okay, finally just a remark, since people are very into probabilities here, about weighting. Since the regular tree languages can have a simple generative model, and the tree homomorphisms are all deterministic, you can weight the tree languages and get a weighted, put probabilities on the tree languages through this kind of obvious generative model. And then you get, you can get a probability distribution over the pairs. That is a joint probability distribution over the string pairs. And you can conditionalize it on one or the other and so forth. So you can get a kind of a weighted version of this system, as long as everything is deterministic, which it is for the tree substitution grammars and tags and so forth. Okay, so let me conclude here. And here are the conclusions that I'm hoping to have convinced you of. That bimorphisms may be a good place to start looking for a universal tree transduction framework. I mean, there are obviously things you can do with bimorphisms. For instance, bimorphisms where both homomorphisms are arbitrary are extremely powerful. In fact, the composition of two of them is Turing equivalent. So that's probably not where you want to look for a universal tree transduction formalism, but this general framework is useful for exploring possibilities.
Sorry, the composition of what is Turing equivalent? Can you just repeat?
The composition of two, this one, B, M, N,
Thanks.
where both are arbitrary.
Got it.
So they're a start for this kind of synthesis. They synthesize synchronous grammars of various sorts with tree transducer theory. They provide a new characterization of both synchronous tree substitution grammars and synchronous tree adjoining grammars as different kinds of bimorphisms, or really, in the case of tag, I have to extend it a little bit to these embedded things. And other applications and extensions fall out naturally, like proofs of symmetry, which you can just read off of the formalism, adding weighting, adding adjunction, and so forth. So let me stop there, and I'm happy to answer any questions you might have. Yeah.
So you talked about bounded rotations as something that we'd like our formalism to do. Now, you might also be interested in unbounded rotations.
That's right.
For example, transforming left branching into right branching trees.
Yeah.
And I was wondering whether the tag version of this will actually do that.
The tag version can, but the TSG version can't.
Good.
And but one reason the tag version can't. So the tag version adds this single argument to each state. This is a special case of something that in the formal language theory literature is called macro tree transducers. But macro tree transducers are much more general. They allow arbitrary arguments and allow you to do kind of arbitrary things to them. So originally, I had thought about using macro tree transducers to get global rotations. But it's kind of using a sledgehammer to get something that's not all that.
So you're pumping at the moment. I mean, you didn't say this, but do you want proposed B of ELC? ELC is the formalism to use?
Well, so no. I mean, I don't think there is. See, the situation is not quite as nice. It really isn't quite. Finite. Well, you just can't beat this finite state stuff. Everything. It's everything. It's closed under everything, and it's just so groovy. And there's no equivalent. Even the people who do tree transducers for a living, not too many of them, but there are a few of them. They're all in Europe. Even they say. I used to put a quote from from a guy who basically said that as for tree transducers, the results don't flow so easily, I think is how he put it. You know, there's too many variations, and they're not all. You do all these variations of finite state things, and they all boil down to the same thing. You do variations on tree transducers, and they're all slightly different. And so I don't know that there's ever going to be the formalism that, you know. And on the one hand, on the other hand, I am trying to take advantage of the fact that we're not trying to do every application. We're just trying to do these kind of natural language things where you don't see a lot of, you know, copying structure all over the place and you know, doing all kinds of complicated checking. It feels much more linear. So I would like to take advantage of that where it's possible.
This is not a question, but I neglected in my introduction to note that Stuart, in addition to all the things that I said and having many awards and fellowships and stuff like that, is also the inventor of with Ibn Chavez, the idea of synchronous grammar. So he was too modest to say that.
Such as it is. Well, I mean, synchronous grammar, that's not strictly true. I mean, so synchronous tags, but
I thought those were the first synchronous grammars.
What's that?
Those weren't the first synchronous grammars?
Well, I mean, you know, people did similar things in the compiler literature before. I mean, they may not have called them synchronous grammar. I mean, the general idea of, you know,
there were tree transducers in the compiler literature, but
well, there's that too. That too. Syntax-directed rewriting is kind of a synchronous grammar. Yeah.
Having thought of these bimorphisms for about 25 minutes now,
it's more than most people.
It looked like, you know, there's like a regular tree language followed by two homomorphisms. In the context of translation, starts sounding a bit like interlingua. Is that the right way to think about it? Or it looks like there's some sort of semantic representation which L might capture.
Ooh, nobody said anything about semantics here. So yes, in the sense that the diagram looks like this instead of looking like this, you're right. But interlingua carries some further baggage that we don't need to import. And the further baggage is that there's something independently characterizable here. But you can imagine, for instance, suppose you wanted to use this for machine translation. What you might want to do, in fact, some people in the audience have proposed this, is induce synchronous tree substitution grammars that, induce tree substitution grammars that are synchronized in this way. But when you do that, you let the chips fall where they may with respect to what synchronizes them. So you're not making any kind of, I mean, the argument for the traditional argument for an interlingua is it's the same one for every language pair. Right? That you're not making any such claim here. You're just saying, well, we'll have two languages and we'll induce this kind of.
Because L is just whatever synchronizes.
Whatever synchronizes these two languages, and if you have a different pair of languages, maybe something else synchronizes them better. I mean, the framework is agnostic. You could also do it. You could also think of this as a. Here's how to think of it as an interlingua. So you're going to erase. You could. I could actually use the same diagram, as it turns out. It's the right shape. You could say, well, so here's the interlingua. And imagine you manually constructed some synchronous grammar that's synchronized to derivation trees now, for some source language and some target language. And then the relation here to the actually derived tree, the parse tree for the source and the parse tree for the target is just a homomorphism. Okay, so if you had this interlingual view of things, and if you had some more languages, you'd be committed to this same one. Now, the composition here is just going to be another homomorphism. So then when you kind of do the composition, you're getting a bimorphism, but now you're committed to really having this be an interlingua. but you don't have to do it that way. You could say, well, we'll just induce one for a particular language pair. So, you know, it all depends on how you use the framework is agnostic about that.
So the role of L is just to synchronize these two, and then it doesn't have to be interpretable in this usual sense.
Right.
Parse tree eventually isn't.
Right. Yeah.
I guess somewhat along similar lines, I'm trying to imagine how constraints on what natural language syntax allows would translate or potentially into restrictions on the nature of these two homomorphisms, so that the class of bimorphisms would be restricted by really substantive syntactic principles. So, I mean, one very vaguely conceived way to do it would be say that if a language, if to get a sentence in German and in English, what you have to do is you start with something like enumeration of lexical items in English, and for each of those there is a corresponding one that's made easy in German, and there's a process of constructing a tree from these lexical items in English. A different process goes on in German, but because they started from something kind of homomorphic, and because there's a limit, there's a sharp restriction on the modes of construction that are available to natural languages, then the relationship between the two is restricted to some class that can be identified. Is there anything?
So there certainly are restrictions. Whether they're linguistically plausible or not is a different matter. Suppose we thought that this relationship was a linear complete homomorphism that is context-free, basically. So the class of tree relations you get then is not arbitrary. There are lots of tree relations you can't get. For instance, you can't get global rotations. So you would then be surprised if you actually saw, if you're committed to this as your view linguistically of how the languages are related, you'd be surprised if you saw two sentences where the natural trees were, one was a global rotation of another. For that reason, it's probably not a plausible linguistic analysis, because there are, arguably at least, global rotations that you find. A little hard to find them, but so you might not want to use that as a linguistic theory. You might still want to restrict for practical purposes, and if you want to do what Jason wants to do, which is induce these kinds of things. Just for expediency, you might want to restrict it for computational reasons or something. But so there are kind of restrictions in the kind of relations you get. And similarly, for if you think that this is kind of a synchronous tag kind of thing, that's not arbitrary tree relations. There are things you can't do. There are tree relations you can't get that way. There, it's more likely that that's a plausible story, because you can do some kinds of global rotation, but you can't go crazy with it. So I have to say, I don't really at the moment have a really good feel for what can and can't be expressed with some of these newer things, like the one with embedded tree homomorphisms and so forth. But it's not everything. It's not this, for instance, even.
So in your list of different restricted kinds of homomorphisms, does one of, if you put enough of those letters together, do you get finite state transducers?
I'm sure you do. What?
Not these letters.
Yeah. I could add some letters, though.
Obviously.
Well, the issue is not actually in the morphisms, right? The issue is in the language in between, which has to only generate right branching or left branching trees, and then you've got it.
Okay, but yeah, we don't have a description of that restriction. But then,
Right.
then the obvious question is, well, can you then compose these things with more powerful tree transducers to get?
Yeah. So actually, bimorphism started as being defined for string transducers, not tree transducers. But as usual, it works out much more nicely with string transducers. Everything always works better with strings than with trees. So there, what you have is instead of tree homomorphisms, you have string homomorphisms, and there, everything works out much. It's like a lot of these different things all amount to the same thing, and so yeah. So the way it works is that the bimorphism, the kind of core of it, instead of being a regular tree language, it's a regular string language, and you apply 2 string homomorphisms to it. Oh, so you asked, could you compose it? I don't know. Might be a way. Might be a way.
Well, probably just
Yeah, I'm sure there
building
is.
on the fact that the composition of a finite state transducer
Yeah.
with a tree transducer is a tree transducer.
Yeah, I'm sure you could. Okay. Thank you very much.